In this video, we will discuss carbohydrates and specifically the organic chemistry of carbohydrates. I bet you know a lot about carbohydrates, so pause please and write down what you know. I wasn't joking. Please pause and write down what you know about carbohydrates. Carbohydrates are also called saccharides or sugars. They have many biological functions, which is why you most commonly encounter carbohydrates in biology class. But guess what? Carbohydrates made out of carbon and water are also organic molecules. And so we will talk about them in organic chemistry class as well. Carbohydrates may be large molecules made out of many individual sugars, and these are called polysaccharides. Fat carbohydrates are polymers, and those monomers are called monosaccharides. All right, let's start to learn more about the organic chemistry of carbohydrates. The learning goals for today are to classify a sugar with structural nomenclature, such as nomenclature that refers to the number of carbons, the functional groups in this sugar, and its reactivity. We will propose complete curved arrow mechanisms for common reactions of sugars, such as those based on acetal chemistry, enol ketotautomerization, as well as general reactions of carbonyl and alcohol functional groups, because, spoiler alert, those are common functional groups in carbohydrates. We will analyze the conformation of cyclic sugars with chair and Haworth projections, interconvert between the Fischer and zigzag conformations for acyclic sugars. Sugars can be cyclic or acyclic. This is the structure of an acyclic carbohydrate. You can see C5H10O5, 5 water molecules, carbohydrate. Here's an acyclic form, and it'll be in equilibrium with the cyclic carbohydrate. I've drawn a monosaccharide. It is one sugar. We'll look at polysaccharides later. And if we wanted to identify functional groups to get started, we can see there's an aldehyde functional group, alcohol, 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 ether? No, that's a hemiacetal. This carbon is this carbon. There's no reagent over that arrow. They're in equilibrium with one another. There's no redox chemistry occurring here. No redox chemistry occurring here. So this carbon has 2 bonds to oxygen in the acyclic form and 2 bonds to oxygen in the cyclic form. So this is not an ether, this is not an alcohol, this whole group is a hemiacetal. Cool, I didn't show stereochemistry of this 5-carbon sugar, which by the way could be ribose. However, we can see that there are several stereocenters. The last learning goal is to predict the optical activity of a sugar or a sugar derivative, speaking of stereocenters and stereoisomerism. So just make sure that you recall that chiral molecules are optically active, which means they rotate plane polarized light, and that will help us when we begin discussing the optical activity, the chirality of sugars and sugar derivatives. Let's get started. We will begin by drawing the structures without stereochemistry for now of the following carbohydrates. Then consider where are these carbohydrates found in nature. There are many terms to know in carbohydrate chemistry, and the first is the ending, the suffix "-ose", which simply means sugar or carbohydrate. And we see it here at the end of the common name glucose. So glucose stands for 2,3,4,5,6 pentahydroxyhexanal. Hexanal, al means aldehyde. So the prefix aldo may be used to describe glucose. It is a sugar containing an aldehyde. In fact, glucose could be described as an aldohexose. Aldo for aldehyde, hex for 6 carbons, and ose for sugar. Next up, fructose. Fructose, ose in the name. It is, in fact, a sugar. 1,3,4,5,6 pentahydroxyhexane 2-one. One tells us that fructose is a ketone, whereas aldehydes must be on the end of the chain. So the al was at carbon 1 for glucose. The number 2 carbon is a ketone for fructose. Because fructose contains this ketone functional group, it is a ketohexose, 6-carbon sugar. So add keto to the carbohydrate terms that you should be familiar with. Hexose, of course, means a 6-carbon sugar. Pentose, of course, means a 5-carbon sugar. In fact, the last sugar that we'll draw out together right now is an aldopentose. And that is 2-deoxyribose, meaning that carbon 2 does not contain hydroxyl. Deoxy, no hydroxyl. Carbon 1 in deoxyribose is an aldehyde. See, carbon 2 does not have a hydroxyl. There are 5 carbons. That makes it a pentose. And again, ose for sugar. You are probably familiar with 2-deoxyribose. It is the D in DNA. Glucose and fructose are constitutional isomers of one another, and both serve as fuel in metabolic pathways, such as glycolysis. We will ignore stereochemistry no longer. We'll begin by reviewing some concepts in stereoisomerism. Please draw all possible stereoisomers of this molecule, then assign the RS configuration of each. There are 2 stereocenters in this molecule, though it is possible that you apply the formula 2 to the n, where n is the number of stereocenters, and predict that 4 stereoisomers of this molecule will be possible. But do recall that mesoisomers must be subtracted from this total number when they exist. And in fact, this molecule has 2 stereocenters that are related by a plane of symmetry in the molecule. I can tell that that might happen because the 2 stereocenters have the same 4 groups: hydroxyl, hydrogen, methyl, and this thing. So there is a possible plane of symmetry that relates the 2 stereogenic centers. And in fact, this isomer is the same as what you may have thought would be its enantiomer. Keeping in mind that for molecules with multiple stereocenters, switching the configuration of all stereocenters generates the enantiomer if the molecule has one, and switching some but not all generate a diastereomer. So redrawing this molecule here, we may have thought that this would be the enantiomer because switch the configuration of 2 groups, change the stereocenter from R to S or S to R, we haven't assigned it yet, and the same with the other stereocenter. However, this molecule, it's the same, represents one of these mesoisomers, molecules with stereocenters that are achiral. They don't have enantiomers. And again, that's due to an internal mirror plane of symmetry. If the carbon 2-3 bond is rotated, the conformation in which the internal mirror plane is evident is accessed. So it's this conformation, the eclipsed conformation of this molecule. It doesn't matter that the staggered conformation is the more stable conformation. This molecule has an internal plane of symmetry. Thus, it is achiral. It is the same as its mirror image. Well, this molecule may not have an enantiomer, but it does have 2 diastereomers. So for molecules with multiple stereocenters, to draw the diastereomers, switch the configuration of 1 stereocenter, but not all. I should say, if there's more than 2 stereocenters, then it's just some, but not all. To draw this molecule, I've switched the configuration of this stereocenter. The final stereoisomer can be drawn by switching the configuration of this stereocenter relative to the first molecule, but also just drawing the enantiomer of the stereoisomer that I had just drawn. I know it's tricky because when you look at these 2 molecules, they look like they should have internal mirror planes of symmetry, but just keep in mind that the carbon chain here is anti. It's an anti-staggered conformation. So right now, there is no mirror plane between carbons 2 and 3 because the methyl down here is not mirroring methyl on the other side of that mirror. So to evaluate if either of these molecules has an internal mirror plane of symmetry, you need to do the same thing we did above, which is rotate around that carbon 2,3 bond. And I'll do that for this stereoisomer. When we do that, we see that in fact there is not an internal mirror plane of symmetry because the hydroxyl that's in the plane is not reflecting the hydroxyl out of the plane. It will be reflecting the hydrogen that's opposite to it. So if I drew the Newman projection, it would look like this. And then I do think we can see that there's not an internal mirror plane of symmetry. Hydroxyl is lined up with hydrogen when the carbon chain is eclipsed. So even though in the staggered conformation that we usually draw these molecules in, it looks like this one might have an internal mirror plane. Once you rotate it into the conformation where that will be possible, you see, no, oops, it doesn't. So it's a bit tricky because this one doesn't look like it has an internal mirror plane, but it does. This one does look like it has one, but it doesn't. And with practice and review from what you learned in Organic Chemistry 1, you will be fine. So these two molecules are enantiomers, non-superimposable mirror images that have all the same properties except how they interact with other chiral substances, like, for example, proteins in the body or plain polarized light. And the other relationships are diastereomeric relationships. Diastereomers have different or can have different chemical and physical properties because they are different. For example, they have different melting points, boiling points, etc. Be sure that you recall the definitions and implications of enantiomeric and diastereomeric relationships. Now let's assign the RS configuration for each stereocenter for each of these isomers. We'll start here. First step, determining the priorities of all 4 atoms bonded to the stereogenic center. Priority is assigned by atomic number. Hydrogen has the lowest atomic number, it's priority 4. Oxygen is priority 1 with the highest atomic number. Carbon versus carbon, we look at what's bonded to those atoms since they tie. This carbon atom is bonded to hydrogen, hydrogen, hydrogen. This carbon atom is bonded to hydrogen, carbon, hydroxyl. This carbon is bonded to higher priority elements, oxygen and carbon versus hydrogens. So that carbon is higher priority overall. Priority 2, priority 3. Now trace the path, 1, 2, 3. The path is going to the right. Just be sure that the lowest priority group is into the page. If it's not, whatever you assign, you need to make opposite. I'll show you that in a second. But in this case, the lowest priority group is into the page. So the configuration is R. We'll take a look at the other stereocenter now. I'll briefly redraw the molecule so that we have a clean slide, clean drawing here. Okay, this stereocenter. The hydrogen is priority 4. The oxygen is priority 1, thinking about the 4 atoms bonded to the stereogenic center. Again, the 2 carbons tie. This carbon is bonded to higher priority elements, so it is priority 2. Methyl is priority 3. Trace the path, 1, 2, 3, right? 1, 2, 3. Now the path is going to the right, but the lowest priority group is coming out, so opposite day, that would be the S configuration of this stereocenter. Relative to this stereoisomer, for its diastereomer, this stereocenter has been, its configuration has been switched, right? So this would have an R configuration, and you can double check that. This one is the same as here, so it would be R. And we've already done the work to assign that. And then both stereocenters have been switched in its enantiomer. Okay, if you need to review how to assign RS configuration, please do that. And when you're ready, move on. How many stereoisomers does this molecule have? Give it a try, and why don't you go ahead and assign RS configuration as well for any stereocenters that it does have. Really pause and give that a shot. As we discussed on the previous page, to determine the number of stereoisomers a molecule has, or the potential number of stereoisomers, the formula is 2 to the n power, where n is the number of stereocenters. This molecule, which happens to be glucose, has 4 stereogenic centers. 1, 2, 3, 4. I've assigned the RS configuration here, but you should really assign it yourself and be sure that what you get come up with aligns with what I've come up with. And if it doesn't, then ask me. So we did say that we needed to account for mesoisomers. If glucose had a mesoisomer, the mirror plane would have to be between carbons 3 and 4 because that would split it in two equal halves. But we can tell that that will not be a possibility here because carbon 6 and carbon 1 have different functional groups. So we would not worry about a mesoisomer for glucose. But let's say if this group were oxidized up to the aldehyde, then carbons 1 and 6 would have the same group. So then I will need to evaluate, is this a mirror plane? But we'll get to that later on in the lesson. Now let's move on and apply the concepts and ideas from stereoisomerism directly to carbohydrates. So this enantiomer of glucose is referred to as D-glucose, and the D has to do with the configuration of the final stereocenter, the lowest priority stereocenter. D is a historical nomenclature that you will learn in biology, but D-glucose is the enantiomer of glucose that is active in your body. Let us now draw the enantiomer of D-glucose. So pause, try yourself. To draw the enantiomer, switch the configuration of each of the stereocenters. So carbon 2 from R to S by putting the hydroxyl from in to out, carbon 3 in to out, carbon 4 in to out, referring to the hydroxyl, and carbon 5 change from out to N. As long as you keep the rest of the carbon chain in the same orientation, then switching just two of the groups will generate the structure of the enantiomer. To draw a diastereomer of D-glucose, we will switch the configurations of some but not all of the stereocenters. There are many, many possibilities here. In fact, there are 14 possibilities because we said there were 16 stereoisomers. One of those is D-glucose. One of those is the enantiomer of D-glucose, which is called L-glucose. L has a different configuration at that final stereocenter than the D. So D refers to our configuration, L to the S. This is a historic nomenclature you can learn about in biochemistry again, but we'll not worry about it here. Okay, so for a diastereomer, there are many possibilities. We will draw one. We'll switch the configuration at carbon 5, and then I'll leave the rest the same. You can try a different diastereomer of glucose on your own. We know that glucose would have 16 stereoisomers due to the 4 stereogenic centers. We discussed that here. The enantiomer of D-glucose, the naturally occurring isomer of glucose, is L-glucose. It's not made naturally, but D is in photosynthesis, and that's amazing that just the one single stereoisomer can be made. So L-glucose has all different configurations of the stereocenter. And then the diastereomer that we drew, it had one different stereocenter relative to glucose. So one, but not all configurations had been switched. That was the 5th stereocenter. So it's a diastereomer of glucose. It's also a diastereomer of L-glucose. And this would be another aldohexose, of which there are, again, 16. And here they are. So we drew an S autohexose because this last configuration was S, so it would be an L sugar. I have here the D sugars drawn. So there are 8 more, the enantiomers of each. Again, we're D, and now it's referring to the configuration of that last stereocenter. If you've taken a biology class before, you've probably seen representations of sugars like this. These representations are called Fischer projections. Fischer projections are a convention for drawing sugars that helps biologists and chemists keep track of all the different possible stereoisomers of carbohydrates. Like we said, for glucose, there are 16. And think about all the different shapes and conformations one could draw glucose in. Unless you were to stop and assign configuration to all the stereocenters, it might be difficult to know exactly which carbohydrate one was referring to. So biologists draw sugars in Fischer projections so that they always can tell which sugar it is. Oh, all 4 hydroxyls are pointing to the right in the Fischer projection. This is D, allose. To properly draw a Fischer projection, the highest priority carbon, which has the lowest number, right? Carbon number 1, that's the aldehyde carbon, the one with the highest oxidation state. The highest priority carbon is at the top of the chain. The lowest priority carbon, carbon number 6, is down here. The carbon chain is oriented vertically, and then the substituents are oriented horizontally. And I will show you how to draw Fischer projection in just a moment with a model. But the carbon chain is basically totally eclipsing itself, and then the substituents, the hydroxyls and the hydrogen atoms, are coming out of the page. I know it's like, what does this mean that she is drawing? I will show you with the model shortly. But if the molecule isn't in the correct orientation as by the convention, then one cannot say, oh, all hydroxyls on the right is D-allose. So it is important to understand the convention and what is meant by this drawing. So the carbon chain is totally eclipsed. The highest priority carbon with the lowest number is at the top. The lowest priority carbon with the highest nomenclature number is at the bottom, and the substituents are oriented horizontally in the drawing. And really what that means in 3D is they're coming out of the page at you. For sugars, D means that the lowest priority stereocenter is pointed to the right, and it will have the R configuration. But understand that D and L is when the lowest priority stereocenter is pointed to, the hydroxyl is pointed to the left of the Fischer projection. So I'll draw out L-allose. I'm drawing the mirror image, right? That's what enantiomers are, non-superimposable mirror image isomers. Right, here's L-allose. Again, the hydroxyl on the lowest priority stereocenter is pointed to the left in the Fischer projection. Fischer projections give us a really nice way to keep track of the stereoisomers of sugars. Instead of assigning R and S, we can say hydroxyls on the right or on the left. And as long as we have drawn the sugar in the correct orientation with the highest priority carbon at the top, the lowest priority carbon at the bottom, then we're all good. This is a great way of keeping track of the 8 diastereomers of these aldohexoses plus their enantiomers. The reason that only the D enantiomers are shown here is because the D enantiomers are the naturally occurring enantiomer. How is it that just one enantiomer naturally occurs when 2 enantiomers have all of the same properties except how they interact with other chiral substances? Great question. That is called the origin of chirality, and it is an active field of thought. Let's move on. So the D in D-glucose is, in all these sugars, comes from D-glyceraldehyde. When these sugars were studied by early chemists, these 4, 5, and 6 carbon sugars were synthesized from D-glyceraldehyde. The process by which they were synthesized is referred to as chain extension. Take a look at D-glyceraldehyde and you can see there's an aldehyde functionality. Aldehydes are electrophilic. And although early chemists didn't use the exact sequence of reactions that I'm going to outline here, I'm going to outline a series that you know from our work together to extend the chain of D-glyceraldehyde. So early chemists didn't use this exact sequence, but similar enough. So the first step would just be cyanohydrin formation. We know cyanide is a nucleophile and it can add to the aldehyde carbon. Now, why use cyanide? Well, it's a 1 carbon nucleophile, and the goal here is to extend the chain, right? So cyanide could add to the top face or to the bottom face of the aldehyde. So it could make this, or it could generate a diastereomer of that molecule. Okay, so you can see going from D-glyceraldehyde to the 4 carbon sugars, the carbonyl carbon now becomes this carbon, and the hydroxyl is either pointed to the right in the Fischer projection or to the left in the Fischer projection. And that's similar to it's either down because cyanide added to the top face of the aldehyde, or it's up because cyanide added to the bottom face of the aldehyde. So these 2 diastereomers resulting from this addition of cyanide to the aldehyde carbon result in these 2 diastereomers of the sugar. Of course, we need to now convert the cyanide, the nitrile functional group, into an aldehyde. Well, you all know how to do that with the reactions we've learned. So the first would just be hydrolysis, by which the nitrile is converted into a carboxylic acid, nitrile to carboxylic acid under aqueous acidic conditions. But an aldehyde is the desired functional group if we're synthesizing these sugars, if we're imagining we're early chemists or chemists that just need to synthesize a sugar. So aldehyde functionality is desired. That will require reduction because aldehydes have two bonds between the carbonyl carbon and oxygen, whereas carboxylic acids have three. We know that esters can be directly converted into aldehydes. So we'll convert the carboxylic acid into an ester. And I'm just working from this one diastereomer. And then for us, we would use a dibal reduction of an ester directly to an aldehyde. These early chemists did not have dibal, but they had other methods of generating the aldehyde. Excellent. A 3-carbon sugar, diglyceraldehyde, has been converted to a 4-carbon sugar by chain extension. So that's what I mean by chain extension, adding a carbon nucleophile in the form of cyanide and then converting that to the aldehyde functionality. The process began with diglyceraldehyde, which is a 3-carbon sugar with 1 stereocenter. Thus, there are 2 possible stereoisomers of this sugar, diglyceraldehyde and its enantiomer L-glyceraldehyde. We can draw the enantiomer of diglyceraldehyde by just drawing its mirror image. L, the hydroxyl points to the left. Diglyceraldehyde is a naturally occurring form of this sugar. By chain extension, diglyceraldehyde can be converted into D-erythrose and D-threose. These represent 4-carbon sugars. They have 2 stereocenters now, and so there are 4 possible stereoisomers. The 2 stereocenters are carbons 2 and 3. Because these 2 sugars are derived from diglyceraldehyde, the lowest priority stereocenter is the same as for diglyceraldehyde. But as we saw in the chain extension, when the nitrile added to the aldehyde carbon, which becomes carbon 2 in the 4-carbon sugars, it could add to either the top face or the bottom face, making one of 2 cyanohydrins. These 2 molecules are diastereomers of one another. So we can see hydroxyl on the right or hydroxyl on the left, and which one of these 2 molecules corresponds to each of these we'll need to figure out once we learn about Fischer projections. So that results in 2 diastereomers. So that counts for 2 of the stereoisomers. The other 2 are the enantiomers, L-erythrose and L-threose, which you could draw as the mirror image isomers of these 2. And just to be clear before we move on, I only showed one diastereomer carried all the way through to the sugar. But we could imagine the same process with the other diastereomer of the chain extended, the cyanohydrin, product of the initial addition to the aldehyde of diglyceraldehyde. And that would give this sugar after this whole process we outlined over here. Okay, so these 2 sugars from the chain extension of diglyceraldehyde represent these 2. We just don't know which is which yet. We will eventually. All right, now these 4-carbon sugars can be chain extended further to make 5-carbon sugars. We're going to add a new carbon on to the carbonyl carbon. So now there's what used to be the aldehyde carbon and erythrose and threose, and that makes 5-carbon sugars. I'm just looking at D-erythrose. When you add on that new carbon, the oxygen becomes a hydroxyl, and it can either point to the right or point to the left, and that makes 2 diastereomers. For the 5-carbon sugars, there are 3 stereocenters. 1, 2, 3. So 2 to the 3, 8 possible stereoisomers. The 4 shown, and they're enantiomers. And these, of course, are diastereomers. They differ in some configurations, but not all. So they all have the same configuration of that lowest priority stereocenter, but you can see they differ in the configurations of these 2. And that's how we define diastereomers. Molecules with multiple stereocenters, where some of the stereocenters have the same configuration and others do not. So to draw a diastereomer, we switch some, but not all of the configurations. So we can see that here in these sugar, more complex examples. Okay, and then finally, extending on to the aldehyde carbon of the 5-carbon sugars, you'll get the 6-carbon sugars. So that carbonyl carbon is now the stereocenter. There were 2 possibilities. That new stereocenter could have hydroxyl to the right or the left. So from each of these sugars, 2 diastereomers are made. And as we've already discussed, 2 to the 4, 16 stereoisomers are possible. These 8 diastereomers and their enantiomers. So D and L, again, come from D-glyceraldehyde, from which all of these sugars can be derived, and they were derived by early chemists who were studying them by chain extension. So by adding on to the carbonyl carbon, of course, carbonyl carbon is reactive. So the D refers to that last lowest priority stereocenter. That one is the same for all of these sugars. Points to the right. That makes them D sugars. They're derived from D-glyceraldehyde. Now let's work on drawing a Fisher projection of D-glyceraldehyde. Recall the convention for a Fisher projection. The highest priority carbon, so with the lowest number. So this is carbon 1. If we were numbering the chain for nomenclature, carbon 2, carbon 3. This is carbon 1 with the highest priority because it is at the highest oxidation state. 2 bonds to oxygen versus 1 bond to oxygen. If you were naming it as an aldehyde, giving this carbon 1, it gives the aldehyde priority. Okay, so that is carbon 1 that has the highest priority and the lowest number. I know that's confusing, so that goes at the top of the chain. There's 1 stereocenter, and then the lowest priority carbon with the highest number, that's carbon 3. It's not a stereocenter, so we don't need to show the substituents on it because it doesn't matter. Now to figure out whether or not hydroxyl should be on the right and hydrogen on the left, or vice versa, hydroxyl on the left and hydrogen on the right, and those are the 2 substituents. That's how I know, that's why I'm saying hydroxyl and hydrogen. We need to orient this molecule as fits with the convention for the Fisher projection. Now, of course, we already know that the hydroxyl should be on the right because it's D-glyceraldehyde, and we know what that means, but pretend like you don't. So the convention is that the carbon chain is actually going into the page, and then the substituents are coming out at you like a dead bug, dead centipede. Let's take a look at that with the model. The first thing you should do is convince yourself that the model is oriented as the molecule is drawn on the page, carbons 1, 2, 3, and the hydroxyl. Molecule is in this odd eclipsed conformation. That's okay. So now we're going to get the model into the conformation of a Fisher projection where the carbon backbone is going into the page and the substituents are coming out towards us. We can see the hydroxyl is indeed pointed to the right, making this D-glyceraldehyde. It's possible that you can imagine just rotating this molecule in space, picking up the hydroxyl or perhaps the carbon chain and rotating it in the same conformation as we did with the model kit to get it in the convention of a Fisher projection. If not, you may have to use your model for a while. So we can, again, the hydroxyl on the stereocenter C2 is on the right. When we put the molecule in, again, the convention of a Fisher projection, this is just a way that people have decided we can orient molecules to draw them and communicate effectively. So now we've drawn the Fisher projection of D-glyceraldehyde. There's the aldehyde, the stereocenter, and the CH2OH, the lowest priority carbon. Now thinking back to the 2 4-carbon sugars that we were considering a few minutes ago, which one of these sugars corresponds to erythrose and which one is threose? Well, it depends on the configuration at the new carbon 2. That used to be carbon 1. So confusing. They will have the same configuration at carbon 3 because carbon 3 was derived from D-glyceraldehyde. So in order to determine the configuration at C2, first orient yourself C1, C2, C3, C4, out of the picture a bit. Orient yourself, make sure the model looks like what is drawn on the paper, and then put the model in the convention of the Fisher projection, so the carbon chain going into the board and the substituents coming out at us, and then we'll see on C2, the hydroxyl is to the right. That makes this sugar, represented by this model, D-erythrose. Convince yourself of that. Be sure that you see it. So carbon 1 is the aldehyde carbon. Carbon 2 does have the hydroxyl on the right. Carbon is right here on the right. Carbon 3, hydroxyl on the right. Carbon 4, not a stereocenter. You might say, but the hydroxyls are anti and the zigzag, so how can this be the Fisher projection? Well, it is because it's a different shape of the molecule, right? This is staggered, this is eclipsed, it's a different shape. So you cannot just look at the relationship in the zigzag and then guess what the Fisher projection is. You actually have to do one of two things. One of them is make the model. Another is just try to rotate on paper. And then I will teach you a shortcut. Yes, now no one cares about anything else with the shortcut. I'll teach you a shortcut in just a moment. So this sugar corresponds to D-erythrose, and then the diastereomer that was made in the process, resulting from these two different stereoisomers, one cyanide added to the aldehyde of D-glyceraldehyde in the chain extension. The diastereomer would be D-threose. And you could make the model of this molecule and convince yourself that it is indeed D-threose. But you'll have to do that on your own. We've looked at molecules with one stereocenter, that was D-glyceraldehyde. We drew the Fisher projection of that from the zigzag. We have taken the zigzag conformations of D-erythrose and D-threose up here and converted those into Fisher projections. Now let's take it up a gigantic notch. Let's take the zigzag conformation of D-glucose and convert it to a Fisher projection. Even if we already know what the Fisher projection looks like, because we can look it up on the internet or it's on the previous page, we should still take the model or try to rotate on paper and see if you can figure out the Fisher projection without looking on the internet. Otherwise, I don't really know what the point of this exercise is. If you like to use a model to draw the Fisher projection, make one and double check with my model. Go ahead, and if you didn't make a model but you still like to work through this exercise, convince yourself that this model represents the molecule drawn in that zigzag conformation here. All the bonds are staggered, and we can see hydroxyl back, hydroxyl back, hydroxyl back, hydroxyl forward, here it is, and then the CH2OH. Then once you've made the model, you want to eclipse all of the carbon-carbon bonds. From there, stretch it out. And by stretch out, you still keep everything eclipsed and the carbon-carbon bonds are still going into the page away from you. And you can see all the substituents are coming out at us like the legs of that dead bug. Of course, except for the 6th carbon, because that is not a stereocenter, so it didn't really matter. And when we do that, we can see, as we probably already knew, for C2, hydroxyl on the right, hydrogen on the left. C3, hydroxyl on the left, hydrogen on the right. C4, hydroxyl on the right, hydrogen on the left. C5, hydroxyl on the right, hydrogen on the left. And double check with the answer. D-glucose down here at the bottom. We got it. Okay, what is that shortcut of which you were speaking earlier? Well, for sugars, you can use the RS configuration to determine whether or not the hydroxyl group will be on the right or left side of the Fisher projection. So for R, the hydroxyl will be on the right side. We already knew this one was because it's a D sugar, D-glucose. And for S stereocenters, the hydroxyl will be on the left. All right, now you know the shortcut. Why are we spending all these time with Fisher projections? Well, 2 reasons. One, because biologists use them, so do biochemists, and many of you will need to be familiar and work with Fisher projections. The other is that they make it really easy to even answer chemistry questions. So for example, imagine that D-glucose and D-galactose have been oxidized at carbons 1 and 6 to dicarboxylic acids. Okay, so if this was carbon 1 of D-glucose, it's been oxidized from an aldehyde and glucose to a carboxylic acid. If this were carbon 6, it's been oxidized from a primary alcohol to a carboxylic acid. Similarly, D-galactose has been oxidized at both carbons 1 and 6. Now, one of these molecules is achiral. How do we know that? Well, because remember all those chemists who were studying sugars, they would oxidize them and look at their properties, and one of those properties is whether or not they rotate plain polarized light. So molecules that rotate plane polarized light are called optically active. Molecules that do not rotate plane polarized light are optically inactive, aka achiral. Of course, that's weird or notable because sugars are chiral, right? They have several stereocenters and typically are chiral. So if one of these molecules is achiral, then it's going to be similar to the situation that we discussed way back at the beginning with this molecule, which had a mesostereoisomer. One of the stereoisomers had an internal mirror plane of symmetry. And remember how we found that? We had to get this in the all eclipse conformation. Well, what exactly is a Fisher projection? Yeah, it's the all eclipse conformation. Yeah, look at that. So Fisher projections make it really easy to see internal mirror planes. Cool. Now, one of these molecules is achiral because one of them does not rotate plane polarized light. So let's put these molecules in Fisher projections and look for the internal mirror plane to figure out which one is achiral. Here are the Fisher projections of glucose and galactose. These molecules differ by their stereochemistries at C4, as indicated here in the Fisher projections. Glucose and galactose are diastereomers. Now, of course, these are derivatives of glucose and galactose, so we'll change up the Fisher projections just a little bit to indicate that. So I'll change the aldehyde and the primary alcohol at carbons 1 and 6 to carboxylic acids. That makes the ends of the carbon chain the same. They have the same functional group. And that means that there might be an internal mirror plane that relates these molecules since all the other carbons have the same functional groups. They all have alcohols. So we want to check between C3 and C4 if there's a mirror plane. So for glucose, I think we can see it's not the case. Hydrogen reflects hydroxyl here. So this is not a mirror plane. Thus, this molecule with many stereocenters, molecule A, a derivative of D-glucose, is expected to be chiral and will rotate plane polarized light, right? 4 stereocenters, it does not have an internal mirror plane of symmetry. Thus, it is chiral and will rotate plane polarized light. However, molecule B, derived from D-galactose, does have an internal mirror plane of symmetry between carbons 3 and 4. The ends are the same. C2 reflects C5 and C3 reflects C4. Although molecule B does have 4 stereogenic centers, it also has an internal mirror plane of symmetry. That makes it what's called a mesocompound, a molecule with stereogenic centers that is achiral because of an internal mirror plane of symmetry. Because this compound, molecule B, is achiral, it is optically inactive. It does not rotate plane polarized light. So Fisher projections are very convenient ways of analyzing the stereochemistry of sugars and molecules derived from sugars. And I've summarized that on this slide. Just to recall how we determined that RS-butanediol was a mesocompound. It was a compound with stereogenic centers that was achiral. We put it in its eclipse conformation. This is the slide that I showed you before we started the analysis of the problem. We put it in the eclipse conformation. We recognized the mirror plane. We said, okay, this is achiral. A Fisher projection is an eclipse conformation, and thus we can easily see internal mirror planes of symmetry in these conformations.